Okay, Organic Chemistry 2330. This is part 3 of our chapter 16, Organic Polymer Chemistry. This we're going to learn about chain growth polymerization. Okay, so in step growth polymerization, we learned we had two functional groups and we typically go AB, AB, and usually we extrude something like water or methanol out of the reaction. Okay. In chain growth polymerization, we tend to add monomer units together without the loss of any atoms, okay? So if we had ethylene, which is 2 carbons and 4 hydrogens, our repeat unit is 2 carbons and 4 hydrogens, forming a carbon-carbon bond. Notice most of the step growth polymerizations form something other than a carbon-carbon bond. Most of our chain growth polymers form carbon-carbon bonds, okay? So this is a very big distinction between step and chain growth polymerization. The other thing we need to look at chain growth polymerization is because we are just adding them together, we're not losing any molecules, we can have a wide variety of things, but most common feature we find in all of these chain growth polymerizations is the fact that we have a double bond, okay? And it doesn't matter whether the thing attached to the double bond is electron donating or electron withdrawing, we can polymerize them all together, all to make a variety of different polymers. For example, if we look at this one right here, polyethylene, that's a really common one. It's used to make packaging materials. Polypropylene is a little bit different, and it's used to make more carbon fibers and textiles. PVC we can use for making plumbing pipes. This with 2 chlorines on there, from the 1 chlorine to the 2 chlorine, it goes to be saran wrap because it actually is a really cool copolymer that allows it to inhibit the transfer of oxygen, which is why it's used in that. Acrylonitrile is used in a bunch of different fibers that are very strong. If we have 4 fluorines on there, we can turn it into Teflon or tetrafluoroethylene system, typically used in very non-stick coatings or high temperature polymer as well. Polystyrene is used a lot for insulating and foams. The polyesters, if we have an ester group on that's been polymerized and it's on the side of it, we're polymerizing the double bond and we're leaving an ester on the side. That's used in a lot of paints. So there are latex paints and also acrylics that we have on for fingernail polish as well. And then we have methacrylates, which are used in transparent glass and bullet resistant glasses as well. So there's a wide variety of different uses for these things, and it's all depending on what else is added to this double bond. Again, electron withdrawing groups, electron donating groups, it doesn't matter. They can all polymerize using this method. Okay, so to polymerize this method, we have to introduce a new functional group that we haven't talked about right now. And we need to introduce it. It's called the radical. Okay, in all the reactions up to now, we've taken 2 electrons and either created an anion or created a cation, or the 2 electrons, and it created a sigma bond. In the case of these radical chain growth polymerizations, we actually are dealing with a single electron that is adds to another system, and therefore this is really, really different than anything we've done before. Because it's different, we actually have 3 different steps that happen during these reactions. We have what we call the initiation step, or the generation of that single electron. We have the propagation step, which is the reacting of that single electron with a double bond, in this case. And then we have the last step, which is the termination, where we get rid of the radicals at the end of the reaction, okay? So in this radical growth, we also need to learn a new type of mechanistic drawing. And in the cases up to now, we've drawn an arrow with 2 barbs on it, indicating we have 2 electrons moving, okay? In the case of radicals, we have to do a different arrow, and that's an arrow with a single barb indicating a single electron. So we call that the fishhook arrow right here. And notice here that we have a bond right here that is number 1 nonpolar, and typically it's something that is 2 very electronegative atoms. For example, it's very common to have 2 oxygens together that you break apart, and 1 oxygen takes 1 electron and 1 oxygen takes the other electron, because instead of having a positive charge and a negative charge, it would prefer to break apart and each have 1 electron each. When we do that, we use a single electron or a single barbed arrow to indicate that one electron has been transferred to each of the oxygens, giving us a radical that we can then further react. Okay, so the first step in our chain growth mechanism is the initiation step. That is the generation of the radical, and we typically use an initiator, a nonpolar bond that we can break apart that has two electronegative atoms. So we can do it with chlorine, we can do it with oxygen. Oxygen is one of the really common ones. And so we need an oxygen-oxygen bond. So we tend to use peroxides, which is an oxygen-oxygen on bonds from an alcohol, or per acids, which is you take two carboxylic acids and you have an oxygen-oxygen bond between them, okay? The next step is what we call the propagation step, and that's where the initiator reacts with the monomer to generate a new radical. And then this continues to propagate and propagate until we get more and more and more and more units on there to make our polymer, okay? So what does that look like, okay? So our initial step is our single electron of our initiator reacts with the one electron of the double bond to generate a sigma bond. That's this sigma bond here. And then the other electron of the double bond generates our new radical, okay? So one electron moved to make a sigma bond, one generated the radical. Now notice we always form the more substituted radical when we do this, okay? We'll talk about that on the next slide. Okay, now that we've generated this radical then can react with another double bond. So one electron from that double bond moves over here to generate a new sigma bond, and we generate a new radical. Okay, so every time this radical reacts with another double bond, it generates one sigma bond and one radical. And that continues and continues and continues until you consume all of the material that have double bonds in them. Okay, so once you've consumed all of the material that has double bonds, that means you start having a higher and higher concentration of these two radicals at the end of chains. When we have a high concentration of that, those two radicals form a sigma bond, and that's how we end the radical reaction. Those two radicals have to combine to form a new sigma bond, and therefore we are terminating our radical. We have no more radical generation, and we terminate the reaction. So step one is initiation of a radical. Step two is a radical reacting on a double bond, creating a sigma bond and another radical. And then the last step is when two radicals combine together to form a sigma bond. Okay, remember I said that the radicals will form on the more stable or most substituted bond. What this means is that our monomer units will add the same way every single time, okay? So in the case of just ethylene right here, we have a CH2 and a CH2. So we don't have any specificity as to which side is which. But we do any substitution here, a chlorine, a methyl group, a styrene, any type of substitution here, and this radical becomes more stable than this radical here. Therefore, it will always react on the incoming radical will always react at the least substituted side, generating our new radical here. This new radical will then react with the least substituted side. So we end up with this very regular system where the head of the one radical reacts with the tail of the alkene, and it continues and continues, and we end up what we call a head to tail linkage. And it's very regular. It always links head to tail, head to tail, head to tail, because we're always generating the more substituted radical in the reaction. Okay, so let's talk about some different polymers that we have from this. The first is polyethylene. It's the simplest, where we just have CH2 double bonded to CH2, okay? And so when we first created this polymer, when polymer chemists first created this polymer, it was turned out it was highly branched, and therefore they called it low density polyethylene because all the different branches kept it from packing very efficiently. So it wasn't very um, crystalline, and therefore it became amorphous and transparent, okay? Now what they figured out was that this material is really easy to process into film by taking the molten polymer and putting it into a heated substrate and then blowing air into it. When it blows air into it, it blows it up like a balloon. While it's blowing it, it's also cooling it down. So by putting in the right amount of pressure, it gets to the same diameter every single time, and then it's folded together and rolled up. So when polyethylene sheet is first made, it's actually it's like a sausage casing, and they have to slit it open one end to get it to actual sheets, okay? So then when they first started this, it's like, well, okay, if it's going head to tail, why does it have so many branch points? Okay, so what they figured out was that there was a possibility, because polyethylene has the same radical on either side, what it was doing was coming back and biting back on itself to generate a secondary radical on the main chain. So if we look at the mechanism here, we have this growing radical right here. It's a primary radical, and it's trying to form that more stable secondary radical. So what it's going to do is it's going to come back with a single electron and generate that secondary radical. When it generates that secondary radical, we now have this little four-membered branch on the side, and then it continues to grow from that side that created the secondary radical. And so we have these little teeny 4 carbon branch points intermittently down the chain. Okay, so now that they learned how that backbinding reaction works, they now can control it to make it so they can have more or less of that chain transfer right here to make it either more dense or less dense. So we can get a bunch of different chemistries from that. Now, one way they learned to control it is by using what they call a Ziegler-Natta catalyst system. In the Ziegler-Natta catalyst system, it does not involve a radical. So by taking away that radical, it's taking away that backbiting, and therefore you get perfectly long chains without that backbiting or that transfer of branching groups, and therefore we can get to high density polyethylene. Okay. And the way they got this to work was they take a titanium catalyst and they react it with this alkyl aluminum compound. And what that creates is this titanium carbon bond. And notice there's a CH3 at the end of this chain, okay? So this is the initiation step. This is where they create this titanium carbon bond. So if we think about it, we have other things that have metal and carbon bonds. And this is always the positive side is the metal, and the negative side is the carbon, okay? So once we create this organometallic compound right here, what we have happen is instead of the radical reaction generating a radical, we have insertion of this into this carbon titanium bond. Notice the CH3 is still at the end of the chain, okay? So the only thing that happens is that double bond, the ethylene inserts into that bond to generate a growing chain, and then we do another one, and 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 that's how we grow out a perfectly long chain with few or no branch points. Okay, so because we got rid of that radical, we got rid of that branching possibility for it. Now that we have this longer polymer chains and they can make a higher density material, they also can be opaque because they can form crystals, or if we cool them down quickly, they'll still stay clear. So when we do high density polyethylene, we typically do what we call blow molding, where we take a kind of like a balloon of the polymer, we take it and heat it up really quickly, blow air into it, and then cool it down very quickly. And what happens is we end up, the heating part will make the polymer plastic. The blowing part fills the mold, and then when it touches the mold's cold enough to make it solidify. And so we end up blow molding into our material here, and it pops out as this solid polymer system. Okay, so that is our introduction to organic polymer chemistry, and that is the end of chapter 16.